Today, in this session, I will cover a topic visual TCAD. Visual TCAD is a device simulation software where we can model different semiconductor devices, starting from basic semiconductor device like PN junction to novel devices like FinFET, nanowire technology, MOSFET technology, SOI technology, anything in semiconductor we can design and we can model and we can check its results. Our software provide an environment where we can model any semiconductor device as well as a small application like if you want to make any small circuit. I will give a brief example. Let's suppose we make a PN junction diode, and the diode application is a small application is a rectifier. So we are giving you an environment where you can make a diode, you can change its dimensions, change its doping, check its results. Then you can use your own fabricated diode as a uh, I mean, you can use your own fabricated diode in designing half wave rectifier. Similarly, you can model different type of MOSFETs like NMOS, PMOS. You can make CMOS circuits. You can make advanced novel devices like double gate devices, FinFET devices, junction left devices, SOI devices. Anything in semiconductor you can design. And once you design your circuit, after means you design your device, after that you can use your device for designing a small circuit may be your 2 transistor to 10 transistor, anything. Small circuit you can design and check whatever the device you have fabricated. Under visual TCAD we have different modules. We have a we have GUI is basically a device drawing environment. Here we do device drawing. Device simulator is Genius 3D. Then we have a 3D modeling tool that name is 3D modeling tool that name is GDS2 mesh. Then we have a workbench module, visual pad. These are the modules that we have in our tool set. Then for advanced, this tool set is you can use up to, you can design up to 14 nanometer technology node. If you want to go beyond 14 nanometer for 3 nanometer to 14 nanometer, we have a tool that name is NDS, Nano Device Simulator. So we are having complete solution for semiconductor device designing. You can, if you want to make a device up to 14 nanometer, you can use visual TCAD environment. And you want to, if you want to make a device lower than 14 nanometer, you can use our advanced module that name is Nano Device Simulator. So in this, how the tool works? Tool work like in visual TCAD GUI environment. First of all, we make a, I'm giving you an example. We make a diode. Anode, cathode. We make a diode. We give this to a simulator. And then simulator will give its IV curve, anode current and anode voltage. Okay. Then once we get the proper IV curve, we convert our device in form of symbol. We convert our device in form of symbol. Then once we fabricate this device. First of all, we fabricate, then we check its characteristics. After getting the characteristics, we convert this device in form of symbol. Then we use this symbol for half-wave rectifier. So all these steps we can do in a tool environment. Similarly, if you want to do, if we are designing any other device like a MOSFET, we can fabricate a MOSFET. We can fabricate PN junction diode and MOSFET, P MOSFET. If you want to make CMOS directly, we can make CMOS. We can make thin film transistors. We can make solar cells. We can make sensors, detectors. We can make advanced novel devices like FinFET. We can make SOI devices, gate-all-around devices. And from all these devices, there are multiple devices we can make here. We can make memories like EPROMs. And once we make all the devices, if we want to use those devices for any application building, we can also make small applications. Small applications like CMOS, logic gates, logic design, like gates, memories like SRAM, flops, flip-flop, anything we can design in the same environment by our own fabricated device. If we fabricate a MOSFET, we want to use our fabricated MOSFET for designing a D flip-flop or SRAM. We can directly use. So we are giving you a complete environment by using the previously shown the module list of a software. So I will give you a live demonstration on my computer machine. So in this demonstration, what I will do, I will cover, I will show you the all this work. Plus, I will demonstrate a MOSFET. So this is a software window. Here we have multiple options: device drawing, device simulation, circuit schematic, text document, XY plot, spreadsheet, visualization. So here, I just want to show you first of all the device gallery. So here you can make our device like this is a simple MOSFET designing. It's a simple MOSFET design. Right. We draw it like this. This one is output of this drawing. This is a drawing structure. We draw the MOSFET like this. I will draw a fresh MOSFET here, but I just want to show you we can draw the MOSFET in 2D, and it will give a output like this. Then we can have a doping profiles. We can have a cut lines, a doping profile like this. We can see the meshing information. You can see the junction information. Everything is visible. We can convert this 2D device into 3D. It will be like this. It will be like this, the 3D MOSFET. the simple MOSFET. We can make advanced structures like this FinFET structure. This is a FinFET structure having a gate. Having a gate at 3 sides. This is a gate. And if you want to see the doping of this structure, move to the doping structure. Below the gate and gate oxide. Okay, so we can create advanced structures like FinFET structures, gate all around structures. This is a gate all around structure. This MOSFET is having cylindrical shape. We can have a structure like this. This is advanced inverted T-shaped structure. This is inverted T-shaped structure. Then all these advanced structures, whatever the structure engineering you want to perform, you can do here. It gives you a free environment. You can change the structure and check its performance. If it is if any performance improvement you find, then you can publish it. And like I will show, this is a vertical nanowire structure. Vertical nanowire structure, right? This is a multi-fin structure. This is having multiple pins. FinFET having multiple pins. I'm just removing the passivation oxide. See the pins. It's SOI. So just remove the bottom oxide also. It's a multi-pin structure having multiple pins. FinFET again. You see, if I remove the nitride, you see the gate all 3 sided. Right. Then not only single device, if you want to make a circuit, you can also make circuit like this. This is a circuit, this is a SRAM circuit. I just remove the substrate part, reset it. This is a complete SRAM that is having 6 transistors. If I remove the top contacts, then vias, see, this is a SRAM having 6 transistors. One inverter is this, second inverter is this, and this is 2 pass transistors having 4 NMOS and 2 PMOS. You can see the NMOS part. These are the NMOS. If I remove the poly also, the NMOS and the PMOS are this is the PMOS. So if you see the doping, this is our inverter. This is our one inverter. This is second inverter, and then pass transistors. So here we can make single devices, novel devices, and then we can also use our devices for small circuit design, like SRAM or maybe any circuit you can design. Now, how we draw this MOSFET here? For drawing the MOSFET, we use device drawing option. Now I'm giving you a complete demonstration. Uh, in device drawing, it depends what type of device you want to draw. We want to draw a MOSFET, so accordingly we make a architecture here. If you want to make any other like double gate or any other architecture, accordingly we have to use these polylines, and we can make the architecture accordingly. So for MOSFET, first of all, I just give you information about the ruler. This plus sign is a center coordinate, and by default the grid size is zero 0.1 micron. 0.1. It depends what type of structure we want to design. Accordingly, we reduce the grid size. 0.1 means 100 nanometer. If you want to reduce it, it will reduce to 0.01 means 10 nanometer. If you want to further zoom it, it will further reduce to 0.001 means 1 nanometer. So accordingly, what type of device you want to design, we have to set the grid size. I'm taking by default grid size initially. Now for making a MOSFET, I take a rectangle box. This, and I make a bottom contact. I make a top contact. Then I have to make a gate oxide. For gate oxide, I use ruler. How much thickness of gate oxide we want? Let's suppose we want gate oxide thickness 5 nanometer. So I just make a ruler to 5 nanometer, 0.0005. You see. Right now, I use again rectangle box. Take a rectangular box again, and I make a rectangular box like this. The edit. This is also 5, 5, 5. One, one, one. Okay, like this. Fine. Now the thickness is 5 nanometer. I just take a polyline again and close it. Our structure is ready. Now we fill a material in this structure. For making it as an NMOS, we click here, add region label. Then we click here, we give the name silicon body, give the mesh size, we select the material. Here we have a list of materials. all type of semiconductor materials are available here. I hope it's visible. All type of semiconductor materials are available here. Connector, insulators are available. Now we choose silicon. Okay, it will add silicon material here. Now here we make a contact. For contact we choose aluminium. For source contact, given source, aluminium. For drain, aluminium. And here give oxide, choose SiO2. Will add, see this portion is shorted, so it will add oxide in the complete region. Now we put gate material and type polysilicon. Okay, now our MOSFET is almost MOSFET material are filled, but it's still not a MOSFET. Mesh size, by I initially say that the by default grid size is 0.1 micron, right? And I will make a mesh first. See, this is a mesh. This is a mesh. It form by default. It will make a mesh, right? How it make a mesh? We give here a limit that it will make maximum mesh size 0.05 micron. So we are just giving them a boundary conditions that it will not increase the mesh size from more than 50 nanometer. Means it will create two parallel lines. This is a device. This device having a mesh like this. And the distance between this is 0.05. That information. Okay. Now this is a MOS. This is still a MOS, but it's not N-type nor P-type because there is no doping. Now we add doping. For make doping, first of all, I just make it transparent. Now it is transparent. Now I add doping. For adding a doping, we click here, add doping profile. There is an option. We click here. Click here. We click here. Uniform doping profile. For making NMOS, we require P-type substrate. So we type and P-type. P means acceptor type. Acceptor. Concentration I'm taking by default 1 is 16 per centimeter cube. Okay. So it means our substrate is P-type dop. Now we want to our channel length here is 0.02 micron, means to approximately 200 nanometer, right? So once we have the MOSFET less than 250 nanometer, we required a threshold voltage implant, right? It means our top surface we require P plus. Substrate is P type, but our top of the surface is P plus, right? So how we do? We do again an implant. Gaussian dop. This implant we call threshold voltage implant, VT. Acceptor. Concentration is bit higher, 1E18. Junction depth 0.1. Okay. So if you see, our top is P plus, right? If you make this structure, I want to see it. You see, here acceptor doping only, so there is no donor. See, surface is P plus and substrate is P, right? The coloring show the concentration of P, the holes is higher. Okay, now I will make now we make it as a NMOS. For NMOS, we require to make source. We have to make source and drain implant N type. So we do. We can click on Add Doping Profile. We select here Gaussian doping, lightly doped, source region, donor 1E18, junction depth 5 nanometer. Okay. Similarly, we repeat for drain, LDD for drain. Source and drain both are identical. So I will do the same thing, whatever we have done there, 5 nanometer. Okay. Now, this is a light dop region. Now we make deep junction implant. Source doping, donor, concentration higher, 20. Junction depth also 25 nanometer. XY ratio I take 0.6. Same thing I do here. Drain doping, donor concentration higher 20. Junction depth 25 nanometer. XY ratio 0.6. Okay. Now if I make a mesh, you see, there's something wrong with this. Things are wrong here because the total device size is very small. It's 0.02. It's not zero point 0.2. It's 0.02 means 20 nanometer. So I have to change everything. Okay. It's very small MOSFET I'm designing. I just define the mesh. Okay. We make a mesh, then we refine the mesh. Okay, now we save this structure.
So did we change?
I'll I'll tell you what I have changed. Actually, I haven't measured the correct distance. My device is very small. It's just 60 nanometer by the size and 20 nanometer the gate size. And my channel length is very small. It's around we can say 18 nanometer, approximately 18 nanometer, 0.18. So I just reduce the junction depth of the doping. I just reduce the junction depth. Since the dimension is very small, so I just reduce the junction depth levels. Okay. So now our device is saved. This is the device that I just saved. Okay. It is having a junction depth. This is the profile of our doping. And this is the profile of our doping in source and drain region. Okay, now I simulate this device. For simulation of this device, I just move to device simulation. Here I load the same device. This device I have saved in this folder. I just load it. Take around a minute time to get loaded. By the time it will load, I will also make one parallel program. Start loading. The device is loaded. Once the device gets loaded, it automatically picks the electrode information. It automatically picks the electrode information. So before this, I just want to show you it's in 2D. Currently, it's a 2D device. Now, if you want to convert this device into 3D, our device name was MOSFET. MOSFET capital letters. .tif file. So we have a program. This is a simple program. In this program, what we are doing, we are taking a TIFF file as an input, whatever the TIFF file we have designed in 2D. We are extending the dimension and we are exporting a 3D file, 3D MOSFET. Okay, let's suppose I will make a MOSFET with take a MOSFET with a width of 0.2 micron. Okay, I just save it and I run it. I run in the same folder. I just minimize it. So what it will do, this program, this program will read the mos.tif file, whatever we have just saved, and it will extend the dimension and save a 3D file by the name of 3D MOSFET.cgns.
What is n dot spaces?
N dot spaces means when we are making a mesh in Z dimension, that we have created a mesh in 2D. Now we are extending the Z dimension.
That is why we're giving Z
So we
dimension.
required meshing also in Z dimension. So we are telling that it will do 8 partition, 8 mesh partition. Okay. So it's running. Finish. So once we check 3D MOSFET, you see. So 8 partition means this. You see, 1, 2, 3, 4, 5, 6, 7, last 8. Okay, 8 equal partition will extend the mesh. So we designed in 2D and we extended it into 3D. Clear? Now I just run this file and simulate this structure. So for IDVG characteristics, I hope you all know about the IDVG characteristics. We first take a linear characteristics. So linear means whenever VT is less than VT. When VD is less than VT, our supply is less than VT, is a linear mode. So we apply a 0.05, 50 millivolt supply to drain, and we ramp gate from 0 to 1 volt in a step of 0.05. So source and substrate are grounded. Okay, we save this file. Okay, now we run it. I'm taking by default values currently. Every value I'm taking by default. This work function I just changed. Work function I will take 4.5. Okay. Models, everything I'm keeping same. I'm not changing anything. I just run it. Run it. We just click on run option. It will ask where I have to run. I will select the folder. I will make one new folder. Give a name run. Okay. It's running. Simulation job submitted. We may open console to monitor the progress. Okay. This is the console. Submitted, connected, running. So here it's running. We get the results here. So what it will do, first it will ramp the drain to 50 millivolt, then start ramping the gate voltage to 1 volt. It's done. Now we select all these results. We do right click, open spreadsheet. Now we get the results in form of this spreadsheet. Here we select what we want to plot. We want to plot gate voltage, okay, gate voltage and drain current. We select both columns. Right click, on x-axis we want gate voltage. We have a IV curve. Our leakage, our off current is this nanoampere range. On is this, okay. Log scale, linear scale, and threshold voltage is approximately 0.2, in between 0.1, 0.18 or 0.2 volt. Now we want to see how the channel is forming. Visualization, electron density in 3D. See, electron density are high at source and drain region. There is no electron density in the channel region, right? But once we run it, start increasing the gate voltage, and you will see the channel start forming. The threshold voltage, the channel start forming. Okay. Fine. Because our supply is very low, so it becomes saturated. The current becomes saturated. See, it is going to be flat. If further increase, it will be flat. So in this way, we can do the simulations. We can check all the things like electric field, electron current, all these properties we are able to visualize. Plus, we can also visualize the band structure. If you want to see the band structure, we have to open result 1 and result 21, these two frames. So what I will do, I will open a 2D visual and I will open these two frames, result 1 and result 21. Here, now here I select conduction band, valence band, ECEV, take a line, cut line, and I put a cut line here. You see the band bending here. Similarly, if you want to plot anything, like you want to see cut line, just cut line. Whatever we want to plot, like potential we want to plot. So we just select the field list, whatever the parameter we want to plot, and we do Control A, and then put a cut line, and Control A again, and just, let's suppose here we want to see the potential. We just draw it, run it like this. You see, when red means when the potential is, when the gate voltage is 0, and 21 means when the gate voltage is 1 volt. How the potential is changing? How the potential is changing? Okay, this thing we can take a data from here, or if you want to see it, want to visualize it, you can visualize it, potential. You see 3D, how the potential is changing. Gate voltage is increasing, the potential is increasing in the channel region. Okay, so these are the 3D views. Now, if we like this result is basically for linear mode. If you want to run again for saturation mode, we again move. We change the gate voltage to suppose 0.8 volt, and we again run it. Yes, in the same folder. Yes. Okay. So this time our gate voltage, our power supply is 0.8 volts, means more than VT. So it will be in saturation. We again, it will first start ramping the drain to 0.8 volt, then start ramping the gate to 1 volt, then 0.8 volt. Now start doing done. Now we open all these results spreadsheet. Now we plot. We will add the result here only. We click on this option, insert curve. Here we select x-axis. We select on x-axis we select gate voltage, and on y-axis we select drain current. Apply. Okay. You see, black one is the previous one, and this in saturation, the on current increases. And if you see the log plot, the leakage also increase. So the channels the size is very small. Okay. Now after this, similarly we can see the visualization, any property, electron density, electric field, potential, conduction band, valence band, whatever you want to see, we can see here. Electron mobility, anything we can visualize here. Okay. Now, if you want to save this device in form of circuit, currently we are doing steady state simulation, IDVG, DC simulation. If you want to do AC, you can change the mode to AC from this option. If you want to do transient, you can change the mode to simulation mode to transient. And if we want to use this our own fabricated MOSFET, we want to make a circuit. We make circuit element. In circuit element, we have it will make a by default rectangle symbol. But if you want to change this symbol, you are free to make your own symbol and save it in the library. Like I will choose different symbol. I will choose NMOS symbol that I have already designed. Now I will, in this symbol, I will lock the pins. S with source, G with gate, D with drain, B with substrate. Now, what I've done, I've designed a MOSFET, I've saved it in ARTIF file, I've simulated, check its characteristics. Now I'm saving this MOSFET file as a symbol file. Now this is my own fabricated symbol, MOSFET.sim, by the name of MOSFET.sim. Now I will use this file, I will close it. I will use this file in circuit schematic. In circuit schematic, I call component, that is numerical device, MOSFET.sim file, whatever the file I have just saved. Okay. Now, if you want to make an inverter, NMOS inverter, I take NMOS by default is a inverter. We just want a resistive load. So I just take a resistive load. Put a resistive load here. Give the value of this load, high value resistance. I just make a connection. The ground, probe, power supply. Now it is just like a ORCAD, but the component that we are using is our own fabricated component. It's not. Now we apply a 1 volt, 1 volt, 3 nanosecond, 6 nanosecond. Now pulse rise time 1 nanosecond, fall time 1 nanosecond. Okay, pulse will see this is not 3 or 8. This is 8 nanosecond. Okay. Now the simulation, the environment is ready. We check the netlist. Netlist is okay. We save it. Inverter underscore NMOS with a resistive load inverter. Now we run it. For how much duration we have to run it? Nanosecond, nanosecond, nanoseconds. So our stop time, I will take 16 nanoseconds, 2 pulses. Step time 0.5 nanosecond, maximum 1 nanosecond. Okay. We save it and we run it. We run it in the same folder, whatever the folder we have created, run folder. Okay. Okay, so here our V1 is the input and prob1 is the output. Okay, we see the results, what results we are getting, whether we are getting a correct inverted curve or not. Start simulation. Initially, if doing operating point simulation, now it is started. During runtime, if you want to plot, we select and we do open spreadsheet. Here we select time, V1 positive and V prob positive. During runtime, we are just updating the results. And we see the input is black and output is pink color. It's inverting. We refresh it. Refresh here. This is the initial condition, so we can ignore it. That's why I'm taking 2 pulses. I'm doing simulation for 16 nanosecond. Perfectly inverted. If you only consider this ramping, it's a perfect DC characteristics of an inverter with TC curve. Still simulation is running. We just refresh the results and again refresh here. Up to 5 nanosecond our simulation is finished. It takes around 2 minutes time to complete this simulation work. After inverter simulation, we are getting these results. This V1 is black one is the input and prob one is basically this pink one is the output. A perfect inverter characteristics we are getting from our own fabricated MOSFET. But this fabrication we have done in 2D. It's not 3D. If we want to fabricate other devices like PN junction diode or anything like SOI devices, like this is simple diode structure. Similarly, we can make any other devices like I will show you here. You can make BJTs. Simple this type of structure we can design here like this bipolar junction. So basically PN junction, BJTs, MOSFET, and if we want to design a CMOS also we can design. CMOS how we design? We design like this a CMOS, a 3D CMOS structure. Okay, this is a way we draw in 2D and we save a 3D file, tip file, and then we extend. Will be a CMOS structure. So similarly, if you want to make any other circuit like AND gate, NAND gate, NOR gate, just increase the layers here. I will show you one of the paper. All papers are published using Our tool like this is a 60 SM using SOI. This is one of the SCI journal, ECS. They make this structure and they make a structure like this. They make a 4 transistors back-to-back inverter like this, then this, and publish and get the first they match the IV characteristics of NMOS PMOS, then they make they make a circuit as a symbol and use for SRAM simulation. This is a complete SRAM kind of chip they make and publish. So they clearly mention the support. You've given them a complete support. They used the tool. There are multiple papers published using the software. Like this is one of the paper. This is my own paper. I'm one of the authors of this paper. This is on HAMT, high electron mobility transistor. Then IEEE papers. I will show some like TCAD. This is from IIT Patna. Gola paper. Tri-gate junction left transistor. They use the tool name Visual TCAD. Mention the tool. They make a similar structure. So now I will show you how to make this type of 3D structure. To design this type of 3D structure, we have to write a script. This we call a DAC file. The script file we call DAC file, and it's just a coordinate system. We have to define a coordinate only in that file. So all these papers are published using our software only. All this stuff. This is one of the latest paper, and I think MRIU is here connected. This all these papers. If you see the thesis work, this is the thesis of IIT Guwahati, and they mention the tool name. They use the tool name. Right. All these papers are published using our tool only. The 4T cell, SRAM cell. This SRAM cell they design in 3D like this. This. So you can use the software for doing your research work, for your publication work. Lot of ways you can utilize the software. Now I will show you how you can make a 3D structure. This, if you want to make a 3D structure like this, it's very simple. Just draw it, save a TIFF file, extend the Z dimension. This is not a real 3D approach. It's basically we are drawing a cross-section view and we are extending a cross-section view kind. It's not a real 3D. For real 3D, like I have shown SRAM. In the starting, I have shown one SRAM cell. That was a real 3D. So I will later explain how to make a real 3D structure. For making real 3D, we have to draw a layout first. Without layout, 3D structure, real fabrication pattern is impossible. But yes, if we want only we want to make only a 3D structure using coordinate, that we can make using a scripting. Like I will show you. This is a simple tri-gate. It's very simple, basic structure in 3D. So this is a way of making. If I show one of more structures, it will be better. Like this is one of the 3D FinFET structure. How we make this structure? We make this structure using coordinate method. This we call a device deck. So we write a script, and in this script, first of all, there is a procedure. The procedure is there are 7 steps we have to follow sequentially, all those steps. So this is bit complicated because here the size of the source pad is larger, drain pad is larger, and the size of the fin is thinner, right? So all this we have given all this shape in coordinates system. Now I will make a very simple structure. I will not take this. How we make this kind of structure? First of all, I just run this. Explain how it will form. Done. op.cns. It's done. Now we open this file. See, it's a very simple structure, very simple 3D structure. Now, how we make this structure? I will take it sequentially. First of all, there are 7 steps. We have to follow them. I just writing here on the board. Rule for deck file. Deck means script. Deck means script. First of all, we make mesh. Here in this we define type and generate, and we define x, y, or z meshing coordinates. First of all, we make mesh. Then second, we fill region. Region we define location, x coordinate, y coordinate, x minimum, x maximum, y minimum, y maximum, z minimum, z maximum, and then a material. First of all, we make mesh. We define mesh type and give the mesh in x, y, and z dimension. Then we write regions in this meshing, on which region we want to fill which material. We give this. Then third, if doping, here also we define regions. In the doping, we also define coordinates, x minimum, x maximum, similarly y, similarly z. Fourth, we define mesh, region, doping. Till here, our device is completed. Means then we export the device. export the device in which format? Dot CGNS or TIFF3D format. Now, if in continuation the 4 steps are required to generate a device, and if in continuation we want to simulate also, using script we generate a device, and in continuation if we want to simulate also, the 5th step is we define models. 6th step is we start biasing. 7th step is results. So for running any program using a scripting method, these 7 steps we have to follow. But if you want to only design a device, within 4 steps we can make our device. Like I have done here in the screen. You see my screen. I have designed this simple rectangle box, or we can say tri-gate. This is one gate, this is top gate, and this is side gate, using the scripting method. So what I have done, first of all, I write a program global T temperature, basically temperature 300 Kelvin, a room temperature we are giving. Then we are defining a mesh, which type of mesh we want. Software support multiple meshing types, so we are using tetrahedral mesh. So we write S_tet4. It's a keyword. Then the tetragen type, it is also keyword. We have to use the same thing always if we are generating a tetrahedral mesh. If we are generating prism mesh, hexagonal mesh, the keyword will change. For that, we have to refer a user manual. Now, we want to design a device. So if we want to design a device, first of all, what dimension we want to design, that calculation we have to done on some paper pencil. Using some paper pencil we have to done. Accordingly, we write a code. So here what we are doing, we write there that we want to make a device of length 0.42 micron, 0.042, 42 nanometer total. So in this device, what we have done, first of all, we write X mesh width 1 means 0.001 means 1 nanometer, and in this we want only 1 species. So if I say 1 species, it means I'm just drawing it. If I explain you this code, I write X mesh. X mesh means we are making a mesh in X dimension. Let's suppose this is X dimension. So we write X mesh width 001. So it will, when we are defining width, it means it will start by default with 0 point, with 0 coordinate. So from 0 to 1, let's suppose it is 0 to 1 nanometer, 0.001, this location is 0.001. It will make only n space, means it will make only one grid line. From here to here, it will make only one grid line. Then width, X width 8. So it will add that one. Means 1 plus 8 means total 9. So in this region, it will make n spaces 4. So in 1, if we add 8 more, the next coordinate will be 0.009. So in this, it will make 4 grid lines. 4 grid lines. Then next 1 nanometer and 1 nanometer. What? 9, 1 nanometer means 10. 0, 1. Width is 1 nanometer. Here the meshing is 5. Then again 1 nanometer means here point is 0.01111. Here again 5. So if you see in this region the n spacing is 5 and width is only 1 nanometer. Why? We want denser mesh. We want to make tight mesh in this region. Right? That's why we give high number of n spaces. Want to increase the number of mesh points. Then n width 20. So in this if we have 20, number of spacing is 20. So it means it is 21, 0.021. Here the number of lines are 20. Then again the mirror image 5541. Then the mirror image of X mesh, right? Then we generate Y mesh. Y mesh means in this location. This is X-axis, this is Y. So top initially we want 2, 10, 2. Means 2 means on the top it is denser. Then here it is lighter. And then bottom it is again tight. This is the way we make a mesh. If you see in this device, in this one, X-axis and Y-axis are visible. You see, here the meshing is very tight. Why? Because in this region we have given multiple lines. It initially will take 1, then 4, then after it 5, 5 meshing. So that's why this is a tight mesh. Because in why we are making it denser mesh here, because we want to make a junction here. This is a NP channel and source junction, or channel or drain junction. That's the region we require. Where we found a PN junction, on those areas we required high meshing. If you see my structure that we have done, this structure, software automatically make mesh in this structure, but if you see this, it make high mesh where it have a PN junction. You see the meshing is high. The same rule we have to follow, and we make a denser mesh at the interface of the junction. So we write a Y mesh accordingly, and then Z mesh, right? How many number of mesh lines we require in Z dimension? X, Y, Z means this one, right? Clear? So we then first of all we make this mesh. Then in this mesh we fill a material. We define our keyword, region, label. Label means whatever the label name you want to give, any name you can give here, and then what material you want to fill, that material, and from which coordinate to which coordinate. We define the coordinate system here. This coordinate to this coordinate we want to fill this oxide. Then which material we want to fill gate material, we have to give a label gate, this, and now from where to where we define the coordinate here. From 10 to x 32. So it means our gates, our channel length is, gate size is 22 nanometer. We define the coordinate, and once we define the coordinate, we fill different material in different coordinate regions. And once it's done, we add doping. Doping is again same. What type of doping we want to do? We want to do Gaussian doping, uniform doping. Like here we are doing uniform doping, acceptor type, donor type, how much concentration, and again the coordinate system. We will define the coordinate, from which coordinate to which coordinate. Okay. Once we write this code and we write export CGNS file or TIFF3D file and we run it. How we run it? We run it like this, run as Genius Deck. Once we click here, it starts simulating this code and make a file op.cgns and op.btu. Like I have opened here, open btu file. It will form this structure. See, n-type regions, p-type, complete p-type, okay, concentrate 118, and one n-type, net doping, if you see, is a net doping region. Clear? Now, once we have this structure, 3D structure, we can simulate it like I have done a simulation in device simulation, either using our previous method, GUI method, or within the same code, we write, attach, drain, we define a voltage source and we attach this and we apply models and we ramp the gate voltage and get the results. Either within the same code we write a biasing, or we can do the simulation using GUI mode also. So it's up to us on what way we are comfortable. Like in this program, we first make a mesh, then we define the region, different regions, then we define the doping, then we define the voltage source, then we attach the voltage source with the device electrode. Then we start ramping the gate from -1 volt to 1 volt, -0.1 volt to 1 volt in step of 0.005, and we're getting the output by the name of gate IB. To run this, we click here, run as Genius Deck. This is a way of making 3D structure using a script. And here the limitation is we are only able to make rectangular shape kind of structure. But if you want to make a cylindrical structure, this mesh type will change. This mesh type will be cylindrical. Like if I will show you. For this cylindrical shape, the code is this. Here, the mesh type is C_3D, cylindrical_3D. And here, instead of X mesh, Y mesh, we have R mesh, means radius of the mesh. R and Z. Z means the length. R means radius. So we define R and Z and we define the coordinate system as same, but here the coordinate is R minimum, R maximum. Plus here we also have one thing, theta, because it's 360 degree cylindrical. So we also have to define theta parameter. Theta 0 to 360, complete round. Then we make a 3D structure like this, cylindrical shape. So all these advanced shapes like like this cylindrical gate-all-around device are possible using scripting. And this is also using scripting. There is one more cylindrical inverter. Yes, this one. The complete uh, vertical gate all around inverter. Both N and P both are stacked. Both are stacked. So this all work is possible using scripting method. Now, if you want to make any advanced circuit like this latch or MOSFET like this, we have to design. Uh, uh, we have to make a layout for this, like we are doing here. If we want to design anything like this latch or SRAM maybe, or like this we want to fabricate a bigger circuit like this. For making this is a D flip flop at 0.13 micron. For this we have to design a layout. For layout we are free, like this is a layout. First of all, we design a layout, then we have a tool that name is GDS to mesh. This tool will read the layout and read the fabrication steps and will fabricate a 3D small circuit like this. It's a small chip like this. SOI circuit, anything you can fabricate. It depends what type of process you want to use. FinFET process, SOI process, CMOS process, bulk process. Whatever you are using, accordingly it will fabricate a device like this. So now I will tell you how to fabricate a device like this circuit. After this session, I will appreciate if you all like the page. Now, for making this type of advanced circuits, okay, let's make a newer one. For making any circuit, what we have to do, we have to design first of all. We have to make a layout first. Like this. Like this. First of all, we have to design, the tool name is GDS to mesh. It's a part of bundle. We have to make a layout. Then we give this layout to the software GDS to mesh and we select the process rule. Then software will implement those process rule on this layout and fabricate a 3D structure like this. You can fabricate any circuit, like this is a D flip flop, image sensor. This is again a D flip flop dice cell. So how we do this? For this, first of all, we have to make a layout. For layout, we have a tool. It's a free tool. You can utilize. You can download this tool from the internet. K layout. Here in K layout, we have to design a layout first. So what I will do, I will first of all I will show you how we do this. Like this is one of the SRAM cell layout. SRAM cell layout. In this SRAM, it is having multiple transistors. I will just disable the extra portion. Yeah. So this is a simple layout having 6 transistors. 1, 2, 3, 4, 5, 6. Okay, these are 6 transistor based SRAM cell. So we design this SRAM cell layout here, and then we give this layout to the software, and software will fabricate and make a 3D structure. So what I will do, I will make a simple NMOS for you, or simple NMOS, or we can say CMOS. First of all, we take new layout, and write CMOS. Okay, here I add the layer property file. Let's suppose I'm using SCL file. I will use layer property file. So this is the layer property file that is having information about each and every layers. So we make a layout here. For making a layout, we pick a layer from here and then make a layout. Let's suppose we take P well first. In Cadence, by default the background is P well, but here we have to make. Okay. Now in this we want to design a NMOS. First of all, we take active. Okay, now NMOS XN. This active is N type, and this active is P type. About this, we have to put a val also because it's P type. Now we take a poly. By default I'm taking by default rules. I'm not taking any perfect geometry. Now I take a contact. Control C, Control V. Okay, now I put a metal M1. This I will take a bulk contact. Here I will make a bulk contact. Bulk contact we take active. Here the for NMOS contact bulk contact is P type, for PMOS bulk contact is N type. Then we put a we take a contact. Move. Now we make a connection here. Metal 1. This is connected. Okay. Now put a one more metal contact. Now we give the naming. Here also we'll add one more contact. Oh, no, not contact, pad only. Port 1. Port 1, port here. Port here. Port here. We give the name. Out. This is out. In. This is in. VDD. This is VDD. VSS. This is VSS. Okay, fine. Now we save this file. CMOS.gds. Okay. Okay. Now this GDS file is saved. We close this. Now we open a tool, GDF2 Mesh 3D model. Here, first of all, we load the process file. I'm using SCL process, so I'm taking SCL process file. SCL process 180 nanometer. Now we load this file, CMOS.gds, SCL process. So here, these are the process parameters: oxide thickness, well doping, substrate doping. All these are the process parameters. So once we create mask, once you click here, software will read the GDS file, whatever we have designed. This software will read the GDS file, and once we click on generate mesh, we write CMOS, click thread, open, okay. It will start implementing the process rules. All those process parameters start implementing on this layout and start fabricating.
So this GBS.
GDS stands for graphical data structure. It's a layout, a mask file. I hope all of you have done know about the layout things. Now the software start implementing the process rules, the fabrication rules on the layout. That layout is a standard format GDS. You are free to use either of this K layout editor, or if you have Cadence, Mentor, any of the soft layout editor software, even Tanner, you can make a layout in any of the software and save .gds file. We require only .gds. If you don't have any layout editor, you can use K layout. K layout is freely available on internet. Just write klayout.de. That is a website. From that website, you can download the layout editor.
So you have to take care of lambda rules while making layout.
Yes, you have to take care, because lambda rules. Currently, I'm just giving an overview. That's why I'm not taking any rules. Now the file is created. You see, it is writing a profile. This file is done. Okay, done. Quit. We quit it, and now we open again the Visual TCAD, and we open the CMOS to 3D file. CMOS. The file is done. This is a surface passivation layer, oxide layer. I just remove this oxide layer. Isolation oxide. I just remove this substrate also. Better clearance. This is the only device we have fabricated, right? If I remove this metal layer, if I remove this contact, this is our device, and if I remove this polysilicon also, and you want to see the doping, this is acceptor type. Currently log is on, enable acceptor type, then donor type. Okay, net doping. See, this is material, our gate oxide. This is a gate oxide, and above the gate oxide, we put gate, polysilicon gate. This is a titanium layer for better conductivity, to reduce the resistivity. The silicon area is large. Then above this we take a contacts. Then above contact, this is a metal and routing, and below is a substrate. And if you see, this is the isolation oxide. Above this is a passivation oxide. Remove the passivation, isolation, and this is a gate oxide is here. If you remove this poly, we are able to see the gate oxide also. So if we, like this, we fabricate the inverter. You are free to fabricate any circuit, any circuit.
So it is much more easier than coordinating. Because in coordination,
There is a see if you are making a CMOS kind of circuits, CMOS process nowadays FinFET process is also very common. We also have FinFET process, like we have done this FinFET based SRAM. This is a FinFET based SRAM. So, but initially there is a one-time effort to write a process file. We are providing up to 12 nanometer FinFET process file here. But if you are making a gate all around structure and you want to make a gate all around process file, we are providing that process, all type of process files along with the software. But if you are thinking some different architecture, then there is a one-time effort. You have to write a process script, and we are using Python. We are using Python to write this process. Scripting is Python. The process scripting is in Python. I will show you all the advanced structures, like if you see, this is a gate stack. This is nanowire, stack nanowire. So this is stack nanowire. From top means either it's 1 nanowire or 4 nanowire. The layout remains same, but we in the process we have to pass a parameter how many stacking we require, how many nanowire we require, like 1, 2, 3, this is 4 nanowires. 4 nanowires are stacks. This is a complete SM, complete circuit. Like how many number of nanowires are required, that from the layout it's impossible to control, but from the process file we are able to control this. Some parameters are using layout, we can control a dimension, we can control the doping, but the architecture, but the architecture we have to write in a script, process script, how the architecture will look like. If you see this structure from you are able to see the contacts. These contacts are wider on the top and narrow at the bottom. So this is the exact way that the fabrication happen. So how we from the layout we are making a rectangular contact, but yes, in 3D we want to create a same profile like it fabricate. So with this we have given this commands in the process file, how the architecture will look like. And if you see this one, the active region where you see it's round edge, and slant. So all these are the all these things we take care in the process file, because this is not a part of layout. From layout is just a top view. So how we can, from our experience, we know that the exact profile, exact fabrication profile is look like this, and there is a rounding. There is a rounding. So that's why we in the code, in the process code, we follow the same pattern. We write a code accordingly. For making this kind of rounding and everything is a simple mathematics. It's not very complicated. It's very simple mathematics. Because nowadays people are working on novel devices, FinFET, nanowires. So why we are working on novel devices? Because we want to make some applications. So we are giving you an environment where you can model novel devices, as well as you can parallelly develop those novel device-based circuit applications. Like this is one of the FinFET SOI FinFET base SRAM cell. And for simulation of all this, the procedure is same. Either we do a simulation using a GUI method, we load in a simulation environment, or if we are making a 3D structure and we want to simulate using a scripting, we can also simulate this structure using a scripting. Like here, first of all, in the tech file, we have a layout, we have a process file. This layout, we just fabricate a 3D structure using this. Then we do a OP simulation, operating point. We load the 3D structure here. Then we define the boundary conditions. Boundary condition, we have to define a solder pad because our device is passivated. Surface, our device surface is passivated. It will be like a packed chip. So if we have a chip, how we provide biasing? Either we put it on a breadboard or either we provide solder contact. So we use the solder contact pad here. The same approach, solder pad to all the electrodes, and then what signal we want to apply to the left. Like for SRAM, we want to apply write 0, write 1, what condition we want to apply. Accordingly, we just connect the supplies, power supply to the boundaries, these boundaries. Okay, and then we do the simulations like we have done for inverter, previous inverter. If you like this demonstration, please like our Facebook page. For Facebook page, you have to open our website, caderdesign.co.in, and here in the bottom there is a Facebook page option is available. Just click on it. The Facebook page will open. We'll appreciate if you like it. I think, yeah, I have to finish it. If any of the center have any query, you can ask me. Before finishing, I just want to show you one more thing. We also have a circuit simulator. It is Simica DE. This software is basically a circuit design tool. And we are providing 2 editions. One is free edition for students. For free edition, you can download this software from our website simica.com. Here is the free edition. Free edition have a limitation. It is for 30 days and having a limitation of 300 elements. And for its complete demonstration, it's you can refer our YouTube channel. You write Simica AMS, analog mixed signal. I have complete demonstration of creating AMS project on Simica tool. So I just run it. You can see it. First of all, we make a library. Simple AMS project. This is for circuit design, analog mixed signal circuit projects. Yes. We make a library, simple AMS project. Here we make a cell. Cell is in this tutorial. We are here all this type of like schematic editor, symbol, Verilog editor, Verilog A, Spice, all this type of cells we can design. So in this project, we are designing 3 different inverter. One is using Spice schematic, other is using Verilog, and third one using Verilog A. It's a complete AMS project we are doing. So we take a symbol from the library. And MOS and PMOS both symbols. And voltage sources. Place the power supply. Ground. We define the voltage source. We are making the pulse source. Here we are also making the same pulse. TD means delay, TR means rise time, fall time, pulse width, pulse period. And now we simulate. We make it variable, VDD. We give the net name. We're doing transient simulation for how much time? In a nanosecond. We give the model. In TCAD simulations, our results are not depending on models. Our results are depending on the material property and the doping we are taking, right? And from the TCAD data, we are in condition to prepare these type of models. Whatever the model we are using in circuit simulations. So this is a pre-extracted model. But if you want to use our TCAD data, we can also use our TCAD data here. Here at input and output, you want to see the out. Just select and we run it. Variable was VDD. Value we are passing 1.3 volt from here. And we run it. This is a simple SPICE simulation. Green one is the input and this purple one is the output. Now we convert this device in form of symbol. We save this state. Now we convert this inverter in form of symbol. We remove this input and power sources and we add pins, input output pins. Now here, what are the symbol we have done? We call that symbol. Now, we again check whether the symbol is giving correct result. Yes, my results are okay. And again save this state. Now we make inverter 2. This second inverter we make using Verilog. So Verilog is currently our, whatever we have done is a pure spice. Now we make inverter 2. This is a Verilog. It's digital, completely digital. So a simple gate level netlist of Verilog. Now here, how we join these two? We first of all we create a symbol for this. This symbol is ready. Now we call this symbol. Now the interesting thing is, previous inverter have VDD input, right? But here we have only two and X input and output, and we are taking a digital block, Verilog block. It doesn't have any power supply sources, and it will take input from previous data. So means we are getting our out one is analog. Here we are getting analog. That analog signal is going. We are going to feed to the digital circuit. Digital, right? So here we do A to D, D to A converter. How we do this? We have, suppose we make out 2, then we have a mixed signal interface. The interface is there. Here we have defined the lower level VDD means 10% of the VDD, and higher level is 70%, 90% of the VDD. Okay, so like this we are giving, it will understand how, where it will found lower signal, low signal or high signal. Similarly to output we want again analog. So we directly define the voltage range 1.3 volt. Now we simulate it. Out 1 also or 2 also we select. Out 2. Now we run it. After A to D, D to A interface element, if we see the last one, the blue one is output. Now a third inverter we make using Verilog A, means we are defining a inverter behavior in analog. We write Verilog A editor. Here we write Verilog A code for inverter. This is a simple code for Verilog A inverter. We again save a symbol, and we call this symbol in the top view. out, give the net name out 3. The properties, here we add the Verilog A code again. And we define the VDD. And we run it by adding the out 3. We add out 3 and now we run it. Now in this project we have analog. See, the yellow one is the again inverted form. Okay, in this project what we have done, we have taken we are showing you an interface how to make a simple AMS, analog mixed signal project, where our first inverter is Spice, second inverter is Verilog, third inverter is Verilog A. Now we are configuring what we want to configure. Which inverter is Verilog A, which inverter is functional. Functional means Verilog. Fine, it's done. Config file means after completing the project, we make a config file so that no one will get changed. Nothing, whatever the parameter we set will not get changed. Okay. If you have any query, please let me know. This demonstration I have already uploaded on YouTube. If you want to see again and again, you just write Simika AMS, and this is a 20-minute demonstration, 10-12 minutes demonstration only. Okay. Thank you.